current consumption rates, global natural gas supplies are projected to last between 80 and 200 years. Unconventional petroleum and gas reservoirs today, about 78% of energy used in the United States comes from petroleum, coal, and natural gas, which traditionally have been the cheapest fuels. However, the price of crude petroleum is subject to very large swings. For example, in inflation-adjusted July 2018 dollars, crude oil rose from a low of $17.48 in 1998 to a high of $161.23 in 2008 before crashing to $49.78 per barrel that same year. Less than 3 years later, in 2011, the price again had climbed to $127 per barrel before again crashing to $30.29 in early 2016. As of this writing, the price of crude oil has climbed back to over $70 per barrel. In the past, many alternative forms of energy have been more expensive to develop than coal or oil and gas produced from conventional reservoirs. However, the cost of producing these alternative forms of energy has been decreasing, while the cost of producing traditional fuels has been increasing. As a result, a major restructuring of the global energy economy presently is underway. Many fuel sources that were uneconomical even a year ago are now economic, particularly given the development of new technologies. Among the biggest of the new changes in the energy economy is the production of oil and gas from unconventional reservoirs. Unconventional reservoirs contain oil and/or gas, but until the past decade or so were not producible using conventional drilling, completion, and production technology. So the type of rock sought by the oil companies has changed from conventional reservoirs in which large pores are filled with oil that has migrated from its source rock to the reservoir where it is trapped. A conventional reservoir might be a coarse-grained sandstone with an abundance of large open pores that are filled with oil or gas. Unconventional reservoirs typically have lower permeability than conventional reservoirs, that is, the pores that contain hydrocarbons in an unconventional reservoir are typically very small and not well connected. As a result, even though the rock is drilled and completed, it is not possible for the hydrocarbons to migrate through the network of tiny pores to the wellbore, and so the hydrocarbons remain in the rock. How small does a pore have to be for a molecule of oil to flow through it? The answer depends on the size and shape of the hydrocarbon molecule and also on the size, shape, and composition of the pore walls. The smallest hydrocarbon molecule that is produced from oil and gas wells is methane, CH, also known as dry gas. Methane is the primary type of gas that is delivered via pipeline to residential homes in the United States for heating and cooking. Methane molecules are 0.414 nanometers in diameter. All other hydrocarbon molecules found in oil and gas are larger than methane, and some are thousands of times larger. Pores that are only a few nanometers across may allow for the passage of methane and restrict larger molecules typically found in liquid petroleum. However, pores that are slightly larger, micrometers in size, are big enough to permit the passage of most hydrocarbon molecules if the molecules don't stick to the pore walls. So most unconventional reservoirs are dominated by very small pore sizes, typically micropores, or a mix of micropores and nanopores. Still, if a single well were to be drilled through this type of unconventional reservoir, the well would not be economically profitable because the hydrocarbon molecules will not be able to negotiate their way through the very elaborate network of natural micropores and nanopores. The reservoir would not release the liquid hydrocarbons. Two major changes in technology, first developed in the U.S. oil and gas industry, have allowed the economic development of very low permeability, tight rock reservoirs that previously had not been possible, directional drilling and hydraulic fracturing. These technologies, explained below, significantly increased U.S. reserves of petroleum and natural gas because it made them accessible at a profitable level. According to the Energy Information Agency, in the next 10 years U.S. production of unconventional tight rock reservoirs will tip the country from a net importer of petroleum and natural gas to a net exporter of both. The first major advance in technology was the ability to control the orientation of the borehole, called directional drilling. For over 100 years since the first successful commercial oil well was drilled in 1859 in Titusville, Pennsylvania, nearly all oil wells were vertically drilled. In the 1970s, a new type of downhole drilling motor, called a mud motor, was developed that did not require the drill pipe to be rotated like a giant drill bit. Instead, drill pipe is pushed down the hole behind the mud motor. Drilling mud, an engineered slurry that is mixed on site, is pumped into the surface end of the drill string. The mud fills the entire interior of the drill string and places an enormous hydraulic pressure on the end of the pipe where the mud motor and bit are placed. The hydraulic pressure causes the motor to spin the bit, and the drilling mud carries the small chips of rock, called cuttings, up the borehole along the outside of the drilling string and all the way to the surface. A well site geologist samples and examines the cuttings at fixed intervals to determine what stratigraphic interval is represented. If a short section of drilling pipe containing a slight bend of 1 or 2 degrees is placed directly behind the mud motor, the borehole that is drilled will be slightly curved. As the well continues to be drilled, the small curve can be continued because a series of small gyroscopes at the leading edge of the drill string allows the inclination and azimuth to be determined and signaled to the driller. The combined information about the total depth of the hole, its inclination, and azimuth is called a survey. By carefully monitoring the hydraulic pressure at the bottom of the hole, the rate of mud circulation, and real-time results from the survey at the bottom of the hole, the driller can control the drilling assembly and maintain the direction of the bend. A bend of 1 degree or less, if maintained as the well is drilled, will allow for a turn of 90 degrees over several hundred meters of drilling depth, so that the borehole changes from a vertical to a horizontal orientation or lands at the desired depth. Once the borehole is horizontal, drilling continues without the bent pipe behind the bit, and the borehole extends horizontally within the targeted geologic layer for 1 or 2 miles depending on the mineral lease. The second major advance in technology that led to the recent development of unconventional tight rock hydrocarbon reservoirs is related to hydraulic fracturing, commonly called fracking. Hydraulic fracturing takes place once the borehole has been drilled, and steel casing is placed down the borehole all the way to its end. Once the casing is in place, the frac crew physically isolates a specific interval of the borehole to be hydraulically fractured, typically near or at the very end of the borehole, and either perforates that interval or opens pre-engineered holes in the casing. This configuration allows the borehole to be filled with a dilute and singularly to the interval of subsurface rock to be fractured. By using high-capacity pumps and large volumes of both water and sand, rock within the isolated interval is fractured, and the grains of sand that had been pumped down the hole are forced into the fractures, propping them open. Eventually, the fracturing stops. Typically, at this point, the pumping of water and sand is paused, a new section of pipe is isolated, and a new fracture set is initiated. Each separately fractured interval is called a stage. Modern directionally drilled wells commonly involve 10 to 30 separate stages. By directionally drilling wells that deviate from vertical to horizontal and then continue to drill horizontally within a single layer of sedimentary rock and then conducting multiple stages of hydraulic fracturing, the reservoir is transformed from one with very low permeability to one with a network of fractures propped open by sand. Moreover, the network of fractures is connected directly to the perforations in the well casing. If the hydrocarbons in the reservoir are under enough internal pressure from their slow conversion from kerogen to liquid petroleum and gas, this artificial permeability network provides the pathway into the well bore and up the casing to the surface. Today, many organic-rich shale units in the United States, including the Marcellus Shale in New York and Pennsylvania, the Eagle Ford and Barnett Shales in Texas, and the Bakken Shale in Montana and North Dakota, are developed by direct horizontal drilling and hydraulic fracturing. Moreover, according to the U.S. Geological Survey, roughly half of the industrial-grade sand that is quarried in the United States today is used for hydraulic fracturing process, providing some indication of the magnitude of this recent shift in exploration techniques. Although directional drilling and hydraulic fracturing have revolutionized the oil and gas exploration industry, particularly in the United States, it has several negative consequences. The first is the large volumes of water that are used in the hydraulic fracturing process. According to the American Geosciences Institute, hydraulically fractured wells typically use over 1 million gallons of water, and most use several million. For reference, an Olympic-sized swimming pool holds 0.66 million gallons, so most hydraulically fractured wells use the equivalent of several Olympic-sized swimming pools. A second consequence of pumping large volumes of water and sand down the borehole is that much of that water subsequently returns up the borehole during the earliest stages of production. Before much oil or gas can migrate through the newly formed network of fractures and into the wellbore, the frac fluid must get out of the way of hydrocarbons passing from the reservoir rock into the well. The fluid that returns to the surface in this initial flow back usually is very salty, contains chemicals left over from the drilling muds, and may contain significant quantities of dissolved or suspended hydrocarbons. The fluid is full enough of pollutants and produced in large enough volumes that the most economic way to deal with it is to pump it down a disposal well. Disposal wells typically are very deep, and some reach all the way to crystalline basement rock. The large volume of frac fluid pumped down disposal wells is forced into the pores of the rocks at the bottom of the borehole. In some places, especially Oklahoma, the deepest parts of oil-producing sedimentary basins contain major faults that are historically inactive but still under significant tectonic stress. Fluid pumped into the pore systems near these faults inflates the pores and can lubricate the fault plane enough to cause it to slip, producing an earthquake. So-called induced seismicity is now common in some oil-producing basins, and the potential for a large earthquake to result is a topic of concern. Coal bed methane. Although most commercial natural gas is produced from conventional reservoirs or through direct drilling and hydraulic fracturing of source rocks, about 7.5% of current U.S. gas production comes from coal seams. There, natural earth heat and microbial activity slowly convert buried coal to coal bed methane, methane that is chemically bonded to coal. Coal bed methane reserves in the United States are estimated to be more than 700 trillion cubic feet, roughly a 5-year supply at current rates of consumption. Most coal beds have a high capacity to store water in small voids in the coal itself. As natural processes convert coal to methane, the gas dissolves in the groundwater within the coal. There, the gas is kept in solution by the pressure of overlying groundwater. Natural gas companies drill thousands of wells into the coal beds and pump the groundwater to the surface, decreasing the pressure on the water remaining in the coal bed. The decreased pressure allows the methane to separate from the water. It is then piped to the surface, where it is compressed and sent to market. Because they store so much water, coal beds are important groundwater reservoirs for farmers and ranchers, especially in the arid and semi-arid western United States, where extensive coal bed methane development is now occurring. However, coal bed methane development has two serious impacts on regional agriculture and ecosystems. The extraction of so much water from the coal beds has depleted essential aquifers and lowered the water table over large areas. Secondly, coal bed water is commonly salty. After it is pumped to the surface, the salt water can poison streams and soils, rendering them useless for agriculture and wildlife. State and federal regulations on water extraction and disposal methods attempt to minimize these impacts. Tar sands. In some regions, large sand deposits called tar sands are permeated with heavy oil and bitumen, a sticky, tar-like hydrocarbon. Crude oil can be obtained from both substances, but these are too thick to be pumped and therefore require other methods of extraction. The richest tar sands exist in Alberta, Utah, and Venezuela. In Alberta alone, tar sands contain an estimated 1 trillion barrels of petroleum, roughly 150 years of U.S. consumption at the 2010 rate. About 10% of this fuel is shallow enough to be surface mined. Tar sands are dug up and heated with steam to make the heavy oil and bitumen fluid enough to separate from the sand. The oil and bitumen are then treated chemically and heated to convert them to crude oil. At present, several companies mine the Alberta tar sands profitably. Once those reserves are depleted, a portion of the deeper deposits, comprising the remaining 90% of the reserve, can be extracted using subsurface techniques similar to those discussed for secondary and tertiary recoveries. Despite its great size, much controversy has surrounded the development of the Alberta tar sands, because the refinement process uses water in very large volumes, which is then expensive to clean prior to being released back into the environment. This controversy has spilled over into the United States, where a major debate involving the construction and completion of the Keystone XL pipeline has involved two U.S. presidents in a months-long protest at Cannonball, North Dakota, which ended in 2017. The Keystone XL pipeline is being built as a shortcut to the Keystone Pipeline System, which is owned by TransCanada and connects the crude oil terminal in Hardisty, Alberta, Canada directly to the Bakken oil fields in eastern Montana and western North Dakota. From the Bakken oil fields, the Keystone XL pipeline will continue southeast to the oil pipeline hub at Steel City, Nebraska, from which the oil will continue southward to refineries on the Gulf Coast. Energy resources, nuclear fuels and reactors. Nuclear fuels are radioactive isotopes that produce heat through nuclear reactions. The heat is used, in turn, to generate electricity in nuclear reactors. Uranium is the most commonly used nuclear fuel. These energy resources, like mineral resources, are non-renewable, although uranium is abundant. Every step in the mining, processing, and use of nuclear fuel produces radioactive wastes. The mine waste discarded during mining is radioactive. Enrichment of the ore produces additional radioactive waste. When a uranium nucleus undergoes fission in a reactor, it splits into two useless radioactive elements that must be discarded. After several months in a reactor, the concentration of useful uranium drops until the fuel is no longer viable. In some countries, spent fuel is reprocessed to recover useful uranium, but in the United States, this process is not economical, so the spent fuel is discarded as radioactive waste. In the early 1970s, the nuclear industry in the United States was growing rapidly, and many energy experts predicted that nuclear energy would dominate the generation of the country's electric energy. These predictions have not been realized. Four factors have led to the decline of the nuclear power industry. Construction of new reactors in the United States has become so costly, in part because of increased regulation, that electricity generated by nuclear power is more expensive than that generated by coal-fired power plants. After major accidents at 3 Mile Island in the United States, Chernobyl in Ukraine, and Fukushima Daiichi in Japan, many people have become concerned about safety. Serious concerns remain about the safe disposal of nuclear wastes. The demand for electricity has risen less than expected during the past 3 decades. After the 1979 3 Mile Island nuclear accident, many plans for the construction of new nuclear power plants were cancelled or suspended, and for 34 years no permits were issued for the construction of new reactors by the U.S. Nuclear Regulatory Commission. Finally, in 2012, the Commission approved permits for 4 new reactors, 2 at an existing nuclear power plant in Georgia and 2 at an existing plant in South Carolina. Since then, the permitting and construction of new nuclear plants has continued. Table 5. 3 is a list of all nuclear power reactors operating in the United States as of April 2017. It is interesting to note that 83 of the 99 total number of operating nuclear plants in the United States in 2017 are located east of the Mississippi River or on the river itself. Only 16 of the 99 reactors are located west of the Mississippi. In addition to the simple need for more energy production in the more densely populated eastern part of the United States, the relatively arid West has easier and more abundant access to other alternative energy sources, especially solar, wind, and geothermal. Outside the United States, nuclear power production has risen rapidly over the past 30 years. Especially in China and Russia. Figure 5.29 shows the total number of operating nuclear power plants worldwide as of 2018 broken down by country. Although the United States still has more nuclear reactors than any other country, others will soon catch up at the current rate of new construction outside the United States versus inside the United States. Between 2015 and 2018, for example, only 1 newly constructed reactor began operations within the United States, compared to 28 new reactors for all other countries. Energy resources, renewable energy: solar, wind, geothermal, hydroelectric, and wood and other. Biomass fuels are renewable, natural processes replenish them as we use them. Although the amount of energy produced today by renewable sources is small compared to that provided by fossil and nuclear fuels, renewable resources have the potential to supply all of our energy needs. As the prices of conventional fossil fuels have risen along with economical, except for biomass fuels, renewable energy sources emit no carbon dioxide and therefore do not contribute to global warming. Solar energy: current technologies allow us to use solar energy in 3 ways: passive solar heating, active solar heating, and electricity production by solar cells. A passive solar house is built to absorb and store the sun's heat directly. In active solar heating systems, solar thermal collectors absorb the sun's energy and use it to heat water. Pumps then circulate the hot water through radiators to heat a building, or the inhabitants use the hot water directly for washing and bathing. A solar cell, or photovoltaic cell, produces electricity directly from sunlight. A modern solar cell is a semiconductor, a device that can conduct electrical current under some conditions but not others. Sunlight energizes electrons in the semiconductor, producing an electric current. Figure 5.30 shows an installation of solar panels. Although solar power still accounts for less than 1% of world energy demand, solar energy is our most abundant resource, and PV cell production is the fastest growing segment of the energy industry. Photovoltaic arrays are now competitive with electricity costs during peak demand times in many desert areas, especially those installed for single-family units. PVs are also cost-effective for electricity needs far from existing power lines. Wind energy in the United States, wind energy grew 1,000%, a tenfold increase, in the decade between 2001 and 2011, and at the time of this writing accounts for 6.3% of the country's total electricity production according to the Energy Information Agency. Wind energy production has grown rapidly because construction of wind generators is cheaper than building new fossil fuel-fired power plants. Wind energy is also clean and abundant. Today, gigantic wind farms generate electricity in Texas, California, and other states, and wind farms are now commonplace in many parts of Europe and elsewhere. The main drawbacks to wind energy include its inconsistency, the conspicuous nature of the wind turbines, the death of birds and bats that collide with the turbine blades, and the noise generated by the blades. In addition, the best places to site a wind farm do not always have large nearby human populations, making it necessary to transmit the electricity generated across a set of power lines which may have to be built along with the wind farm. Economic and environmental costs are incurred by building new transmission lines, and the loss of electricity transmitted long distance is an economic consideration that limits the development of wind farms. Geothermal energy extracted from Earth's internal heat is called geothermal energy. Geothermal plants typically collect underground steam from geysers, volcanoes, and hot springs and use the steam to spin turbines, which generate electricity. Naturally hot groundwater also can be pumped to the surface to generate electricity, or it can be used directly to heat homes and other buildings. Alternatively, cool surface water can be pumped deep into the ground, to be heated by subterranean rock, and then circulated to the surface for use. The United States is the largest producer of geothermal electricity in the world, with a production capacity of just over 3 gigawatts. In the United States, most geothermal plants are located in the western states, because the region is more tectonically active and the geothermal gradient is higher. We will learn about tectonics in Chapter 6. The oldest, and also presently the largest, steam-driven geothermal plant in the United States is located at the Geysers, about 72 miles north of San Francisco. That plant alone is capable of generating 1.5 gigawatts of electricity, enough for about 375,000 average U.S. households. Relative to other renewables such as wind and solar, geothermal energy can be used 24 hours a day, 7 days a week, so it has a larger capacity factor, a measure of the amount of the actual output of energy to the total possible output over some period of time. Because the wind does not blow all the time and the sun does not shine all the time, these energy sources have a lower capacity factor. Hydroelectric energy: if a river is dammed, the energy of water dropping downward through the dam can be harnessed to turn turbines that produce electricity. Hydroelectric generators supply roughly 19% of the world's electricity. In the United States, about 7% of our electricity comes from hydroelectric power. Although hydroelectricity is renewable, it is entirely dependent on adequate runoff, and recent climate change has caused many of the large reservoirs in the western United States to be drawn down significantly. Inadequate runoff lowers the capacity factor of hydroelectric generating facilities. In addition, the construction of dams and formation of reservoirs destroys wildlife habitats, agricultural land, towns, and migratory fish populations. For example, the dams on the Columbia River and its tributaries are largely responsible for the demise of salmon populations in the Pacific Northwest. Undammed wild rivers and their canyons are prized for their aesthetic and recreational value. Large dams also are expensive to build, and few suitable sites remain. For these reasons, the United States is unlikely to increase its production of hydroelectric energy. In fact, many historic dams, including some with hydroelectric power generating capabilities, are being removed. Biomass energy: biomass fuels provide many sources of energy. The burning of wood as a source of heat is familiar to all of us. Today, wood and agricultural products also are burned for the generation of steam and electricity at the industrial level. Additionally, biomass from oil-rich plants such as canola or corn are converted to liquid form to use as transportation fuels, such as ethanol. Much research currently is being directed toward the production of liquid fuels and other chemicals from biomass. Biomass energy can be produced domestically in most countries, thereby creating local jobs and reducing foreign oil imports. However, production of biofuels is not always a net energy gain. In some cases, more energy is used in the production and processing of these fuels than can be extracted from them. In addition, burning of biomass produces carbon dioxide, a greenhouse gas, and releases particulates and other pollutants into the atmosphere. Transmission of electricity: the hidden costs. The building of new renewable energy plants, such as wind or solar farms, geothermal, hydroelectric, and biofuels plants all are based to some degree on the availability of the energy resource itself. Wind farms need wind, solar farms need sun, geothermal plants need geothermal energy, and most biofuels are generated in low-population agricultural regions. These places of energy resource availability usually don't correspond to a large local population of humans, so it is usually necessary to transmit the electricity generated in each of these cases to the cities and their associated industrial zones. Installing new long-distance transmission lines is very expensive economically and very disruptive environmentally. In addition, the transmission of electricity itself requires energy, because the transmission lines lose energy through heat loss as the electrons pass through it, a phenomenon called the Joule effect. The Joule effect results in loss of between 8 and 15% of electricity during transmission across long distances. This loss is in many cases enough to render what might otherwise be a good site for a wind or solar farm or a new geothermal plant uneconomically feasible. The future of renewable energy resources, according to the 2018 Annual Energy Outlook published by the U.S. Energy Information Agency, the mix of energy fuels both produced and consumed by the United States will change between 2017 and 2050. On an absolute basis, the consumption of natural gas as an energy source will grow the most during this period, but the development of non-hydroelectric renewable energy resources is projected to be the fastest-growing segment of the energy economy in percentage terms. Much of this growth in non-hydroelectric renewables will offset the continued decline in the production of nuclear energy, but the percentage of overall energy produced in the United States by non-hydroelectric renewables will remain small compared to that produced by natural gas. In addition, the agency forecasts that strong petroleum production coupled with relatively flat demand will allow the United States to become a net energy exporter within the next decade. Nearly all of the energy exported by the United States is projected to be in the form of petroleum and natural gas, and recovery of hydrocarbons mostly from tight oil reservoirs. The southwestern United States is expected to lead the growth in U.S. tight oil supplies between 2017 and 2050. In contrast, the eastern United States along with the Southwest is expected to lead the growth in natural gas production because tight gas reservoirs there are relatively shallow and widespread, an abundance of pipelines already are built, and there is a large population base to consume the gas and a coast to export it. The global picture of energy production and consumption over the next several of decades is projected to be somewhat different than that of the United States. According to the International Energy Outlook published in 2017, between 2015 and 2040, world energy consumption is projected to increase by 28%, with more than half of the increase attributed to growth in Asia, especially China and India, where strong economic growth drives increasing energy demand. Global energy consumption is expected to increase for all major fuel types except coal, with renewables growing at the fastest rate. Global consumption from natural gas, petroleum, and nuclear all are projected to grow through 2050, despite the slowdown of nuclear reactor construction in the United States. The strong future growth projected for renewables through 2050 is forecast to lead to an increase in the global production of electricity from 21% in 2015 to 29% in 2050. Even with the projected decline in energy produced from coal, global energy production is projected to be dominated by petroleum and natural gas. Conservation as an alternative energy resource. The single quickest and most effective way to decrease energy consumption and to prolong the availability of fossil fuels is to conserve energy. Policies to improve energy efficiency are more cost-effective than building new power plants. Such policies help to reduce air pollution and dependence on oil imports while saving money for consumers and industry. Energy conservation has helped to produce dramatic results in the United States, where expenditures for energy as a percentage of gross domestic product fell from about 13.5% of GDP in 1980 to about 6% of GDP in 2000. Higher global energy prices since 2000 have caused expenditures for energy to rise again, to over 9% of GDP, despite the fact that the amount of energy used per person in the United States has fallen by about 12% over the same time period. Clearly, conservation is a critical component of keeping the total expenditure for energy in the country from continuing to rise. Some energy experts have suggested that if people in industrialized nations use more efficient equipment and develop more efficient habits, these nations could conserve as much as half of the energy they consume. Energy use in the United States falls under three categories: buildings, industry, and transportation. Two types of conservation strategies can be applied in each of those categories. Technical solutions involve switching to more efficient implements. Social solutions involve decisions to use existing energy systems more efficiently. Technical solutions: buildings in 2017, residential and commercial. Buildings consumed about 39% of all the energy produced in the United States. Most of that energy was used for heating, air conditioning, and lighting. Significant energy savings are possible in all aspects of energy consumption in buildings. As one example, lighting accounts for about 20% of the average U.S. home's electricity bill. Because incandescent lighting is about 95% inefficient in energy consumption, savings in that area alone are potentially great. A fluorescent bulb consumes 1/4 as much energy as a comparable incandescent bulb and can last 10 times longer. In addition, new solid-state technology promises further advances in energy-efficient lighting. For example, light-emitting diodes are lights that are illuminated by the movement of electrons through a semiconductor. There is no filament as with incandescent lights, and LEDs release almost no heat, so they are much more efficient, last much longer, and use far less energy. Today, LEDs are used in clock radios, jumbo TVs, and many other applications. According to the Department of Energy, widespread switching to LED lighting technologies over the next 15 years could save the equivalent annual electrical output of 44 years by large electrical power plants. Industry consumes about 31% of the energy used in the United States. In general, conservation practices are cost-effective, and many companies are taking advantage of the fact that saving energy is profitable, although industry still wastes great amounts of energy. For example, about 2/3 of the electricity consumed by industry drives electric motors for machinery and tools. Most motors are inefficient because they run only at full speed and are slowed by brakes to operate at the proper speeds to perform their tasks. This approach is like driving your car with the gas pedal pressed to the floor and controlling your speed with the brakes. Replacing older electric motors with variable speed motors would save vast amounts of electricity, but such replacement has been slow. Transportation. About 28% of all energy, more than 50% of the oil usage in the United States, and 1/3 of the nation's carbon emissions are consumed for transporting people and goods. The efficiency of standard gasoline-powered auto and truck engines is about 10%. Thus, we can save much energy by using more efficient cars and trucks. Over the past few decades, automobile manufacturers have offered vehicles with increasingly efficient internal combustion engines. Other avenues that auto companies are exploring include electricity and hydrogen power. A hybrid car uses a small, fuel-efficient gasoline engine combined with an electric motor that assists the engine when accelerating. Hybrids consume less gas and produce less pollution per mile than conventional gasoline engines. Current models of hybrid cars achieve fuel efficiencies ranging from 51.48 to 31.27 miles per gallon, depending on make and model, and they produce as much as 90% fewer harmful emissions than a comparable gasoline engine. Using hybrids and other energy-efficient vehicles, American motorists could achieve a 50% or greater increase in fuel economy, the equivalent of about 1/3 of current oil imports. Another solution is the electric car. Battery-only and gasoline, electric hybrid cars have seen a recent increase in popularity and availability. If that trend continues, perhaps we can further reduce the cost of and dependence on petroleum. Challenges associated with battery-powered vehicles include the need to recharge the battery and draw energy off the electrical grid to do so, and the availability of key mineral resources needed to build the batteries, especially the element lithium. According to the 2018 Mineral Market Summary, published by the USGS, lithium supply security has become a top priority for technology companies in the United States and Asia. Strategic alliances and joint ventures among technology companies and exploration. Companies continue to be established to ensure a reliable, diversified supply of lithium for battery suppliers and vehicle manufacturers. In 2017, the most recent full year for which data are available, the United States imported more than 50% of its lithium, mostly from Argentina, Chile, and China, which along with Australia are the world's top 4 producers of the element. Indeed, in less than 2 years between February 2016 and January 2018 alone, the world lithium price went from a record low to a record high, jumping nearly 150% in the process. Lithium is mainly produced from a type of granite with extremely coarse crystals and rare minerals with rare elements. Pegmatite is an igneous rock that crystallizes at the final stages of cooling of a body of magma to a pluton. The last bit of magma to cool contains an abundance of otherwise rare elements, like lithium and uranium, that do not normally fit into the crystals of common rock-forming minerals that make up plutonic rocks formed during magmatic cooling. Minerals crystallizing from these late-stage magmatic fluids do incorporate these unusual elements, including lithium, into their crystal structures. Pegmatite, the rock containing these minerals, is one major source of lithium. The other source is from deep underground brines that must be pumped and processed for the lithium to be recovered. Social solutions involve altering human behavior to conserve energy. Energy-conserving actions can be used in buildings, in industry, and in transportation. Some result in inconvenience to individuals. For example, if you choose to carpool rather than drive your own car, you save fuel but inconvenience yourself by coordinating your schedule with your carpool companions. High mileage. Cars are on the market, but they will make an impact only if people make the social decision to use them. People argue that this social decision comes at a cost because light vehicles make the driver and passengers more vulnerable in case of an accident, but studies have shown that lighter, more agile vehicles, with better turning capacity and more effective braking, are actually safer than heavier SUVs. An example of a modest change in lifestyle that could have a major positive impact on the balance between production of mineral and energy resources and their consumption and the environmental impacts of both is the role that plastics play in our society. From plastic straws and cup lids to children's toys, modern fabrics, car parts, and even satellite dishes, our society consumes plastics at a voracious rate, and the consequences are only recently being brought to light. All plastics are made from hydrocarbons. Plastics are not grown, nor are they mined. Ultimately, all plastics are synthesized from crude oil through chemical engineering. Not many people realize that their outdoor fabrics mostly are derived from crude oil, let alone their drinking straw. The gigantic volume of plastics that are consumed globally has had a significant negative impact on the global environment because much of the consumed plastic ends up as waste that must be disposed, and a large amount finds its way into the environment as litter. Disposing of plastic through incineration generates a variety of toxic chemicals that are released into the atmosphere. Plastic that ends up in the environment as litter has accumulated in famous giant collections at certain spots in the middle of the ocean, where ocean currents create a sort of slow vortex that draws in floating garbage. In addition, when exposed to the environment, plastics break down to microplastics, tiny pieces of plastic, that are commonly mistaken for food by small vertebrates and invertebrates. Microplastics are having a large negative impact on the ocean ecosystem because it can fill the digestive gut of small organisms that mistake the floating bits of plastic as food and eat it. Eventually, the organism dies because its plastic-filled gut causes it to starve. Today, awareness of the negative consequences of using so much disposable plastics in our society is increasing. For example, a recent campaign to never again use a plastic straw has been launched with the clever slogan, "Don't suck." It is through awareness campaigns like this, along with individuals following through with necessary changes in behavior, that humans will be able to reverse some of the negative consequences of our throwaway society. Energy for the 21st century. Is it possible to alter global energy production from a fossil fuel economy to an economy of renewable energy resources? In 2001, the UN's Intergovernmental Panel on Climate Change concluded that significant reduction of fossil fuel use is possible with renewable technologies that exist in operation or pilot plant stage today, without any drastic technological breakthroughs. In other words, they suggested that if we vigorously develop all the renewable energy resources listed in section Energy Resources, nuclear fuels and reactors, the global economic system could absorb a drastic decline in petroleum production without massive disruptions. A year later, 18 prominent energy experts published a rebuttal in Science, proposing the exact opposite conclusion. Using almost the same phrases, with the simple addition of the word not, they argued that energy resources that can produce 100 to 300% of present world power consumption without fossil fuels and greenhouse emissions do not exist operationally or as pilot plants. Their basic counterargument is that global energy consumption is huge and renewable sources have low power densities. Thus, we do not have the available land, nor could we quickly build the required infrastructure to replace fossil fuels. In 2011, the IPCC again argued that close to 80% of world energy supplies could be met by the continued growth of renewable energy, provided they are backed by policies that enable their development. 4 years later, in 2015, the IPCC aggregated the risks posed by continued increases in global temperature into 5 reasons for concerns. The IPCC went on to say measures exist to achieve the substantial emissions reductions required to limit the likely warming by 2 degrees, and that it would require 40–70% reduction in greenhouse gas emissions by 2050 and near zero emissions by 2100. When experts disagree, it is difficult for laypersons to evaluate the merits of the contradictory arguments. But whoever is right, it is clear that if global energy demand significantly exceeds supply, the world will fall into unprecedented economic chaos. Commerce will slip into unimaginable depression. Food supplies will diminish, and food distribution will become expensive. Poor people, who are already on the edge of malnourishment, will starve. On the other hand, if we continue to base our future energy economy on hydrocarbons and ignore or fail to adequately mitigate the environmental consequences of global climate and environmental change that come with it, we risk pushing Earth's systems past the point at which the ongoing mass extinction will ultimately involve us. We can only hope that human ingenuity will combine with economic and political commitment to develop alternative energy resources before these catastrophes become reality. Chapter 6: The Active Earth. The origins of continents and oceans. About 5 billion years ago, a ball of dust and gas, one among billions in the universe, collapsed into a slowly spinning disk. The inner portion of the disk condensed to form our sun, while the outer parts coalesced to form planets orbiting the sun. Our Earth is one of those planets. Earth began to form as particles of dust and gas were drawn together by gravity and began to collide. These collisions caused the coalescing particles to become hotter and hotter. Frozen crystals of carbon dioxide, methane, and ammonia melted as the spinning mass, early Earth, slowly heated up. Eventually, ice melted. The young planet grew hotter as asteroids, comets, and other space debris crashed into its surface. Additional heat was released by the decay of radioactive isotopes within its interior. By about 4.6 billion years ago, the planet became hot enough that it melted. Then, as the bombardment slowed down and radioactive isotopes decayed and became less abundant, much of Earth's heat radiated into space and our planet began to cool and solidify. Today, although Earth's surface has cooled to temperatures that support living organisms, the interior remains hot, both from heat left over from the early melting event and from continued decay of radioactive isotopes. Consequently, Earth becomes hotter with depth. At its center, the Earth is close to 7,000 degrees Celsius, similar to the temperature of the Sun's surface. This internal heat causes earthquakes, volcanic eruptions, mountain building, and continual movements of the continents and ocean basins. These effects, in turn, profoundly affect our environment, Earth's atmosphere, hydrosphere, and biosphere. Earth's internal heat engine and its effects are described in the theory of plate tectonics, a simple theory that provides a unifying framework for understanding the way Earth works and how Earth systems interact to create our environment. The term tectonics is taken from the Greek tektonikos, meaning construction. Like most great scientific revolutions, the development of plate tectonics theory developed incrementally over many years, building on earlier observations, hypotheses, and theories. The story illustrates how a scientific theory evolves through the accumulation of evidence and how scientists rely on the work and discoveries of earlier scientists. Alfred Wegener and the origin of an idea, the continental drift hypothesis. Although the theory of plate tectonics was not developed until the 1960s, it was foreshadowed early in the 20th century by a young German scientist named Alfred Wegener, who noticed that the African and South American coastlines on opposite sides of the Atlantic Ocean seemed to fit as if they were adjacent pieces of a jigsaw puzzle. He realized that the apparent fit suggested that the continents had once been joined together and had later separated by thousands of kilometers to form the Atlantic Ocean. Wegener was not the first to make this observation, but he was the first scientist to pursue it with additional research. Studying world maps and making paper cutouts of each continent that he could move around, Wegener realized that not only did the continents on both sides of the Atlantic fit together, but other continents, when positioned correctly, fit like pieces of the same jigsaw puzzle. On his map, all the continents joined together formed one supercontinent that he called Pangaea, from the Greek root words for all lands. The northern part of Pangaea is commonly called Laurasia and the southern part Gondwana. Wegener understood that the fit of the continents alone did not prove that a supercontinent had existed. He began seeking additional evidence in 1910 and continued work on the project until his death in 1930. One line of evidence Wegener found in support of his hypothesis is the occurrence of uncommon rock types or distinctive sequences of rocks that are identical on one side of the Atlantic Ocean and the other. When he plotted the distinctive rocks on a map of Pangaea, those presently on the east side of the Atlantic were continuous with their counterparts on the west side. For example, the deformed rocks of the Cape Fold Belt of South Africa are similar to rocks found in the Sierra de la Ventana Fold Belt of Argentina. Plotted on a map of Pangaea, the two sequences of rocks appear as a single, continuous belt. Using fossil evidence to support the existence of Pangaea, Wegener compiled information regarding locations of certain fossil plant and animal species that could neither swim well nor fly, so were unlikely to survive long oceanic crossings. Today, these fossils are found in Antarctica, Africa, Australia, South America, and India, all of which are separated by wide oceans. However, when Wegener plotted the same fossil localities on his reconstruction of Pangaea, he found that they all occurred in the same region. Wegener deduced that rather than migrating across the wide oceans that presently separate the different fossil locations, each species had evolved and spread over a portion of Pangaea before the supercontinent broke apart. Wegener also cited evidence from sedimentary rocks known to form in specific climate zones to support the existence of Pangaea. Glaciers and gravel deposited by glacial ice, for example, form in cold climates and are therefore typically found at high latitudes and high altitudes. Sandstones that preserve the structures of desert sand dunes form where deserts are common, near latitudes 30 degrees north and south. Coral reefs and coal swamps thrive in near-equatorial tropical climates. Thus, each rock type reflects an ancient environment characteristic of a specific latitude. Wegener plotted 250-million-year-old glacial deposits on a map showing the modern distribution of continents. Notice on this map that glacial deposits would have formed in tropical and subtropical zones. Figures 6.3b and 6.3c show the same glacial deposits and other geological indicators of climate plotted on Wegener's Pangaea map. In Wegener's reconstruction of Pangaea, the glaciers cluster neatly about the South Pole, coral reefs and coal both occur in equatorial position, and desert environments formed around 30 degrees north, similar to the modern distribution of these paleoclimate indicators. Wegener's concept of a single supercontinent that broke apart to form the modern continents is called the theory of continental drift. Wegener first presented the framework of his theory in 1912 and published a more thorough treatment in 1915 in the first edition of his book The Origin of Continents and Oceans. In one of the great examples of scientific feudalism, the reaction to Wegener's hypothesis was overwhelmingly negative and in some cases exceptionally scathing. Thomas Chamberlain, geology professor at the University of Chicago, wrote, "Wegener's hypothesis in general is of the footloose type, and is less bound by restrictions or tied down by awkward, ugly facts than most of its rival theories." Stanford geology professor Bailey Willis remarked, "Further discussion of merely encumbers the literature and befogs the mind." The strongly negative reaction to Wegener's ideas regarding continental drift was the result of three factors. First, Wegener did not provide alternatives for his theory of continental drift, so some scientists viewed his approach as subjective, biased, and downright unscientific. Second, in the early 20th century, many geologists had begun to turn away from traditional field-based observations toward more detailed, quantitative laboratory measurement of rock properties. As a result, many scientists considered Wegener's field-based evidence to be old-fashioned, unsophisticated, and vague. Third, and perhaps most importantly, Wegener had concentrated on developing evidence that continents had drifted and not on exactly how they could move. Perhaps as an afterthought to what he considered the important part of his theory, Wegener suggested two possible mechanisms to explain how continents moved: that continents plow their way through oceanic crust, shoving it aside as a ship plows through water, or that continental crust slides over oceanic crust. Physicists quickly proved that both of Wegener's mechanisms were impossible. Oceanic crust is too strong for continents to plow through it. The attempt would be like trying to push a paper boat through heavy tar and would deform the continents into an unrecognizable state. Furthermore, frictional resistance is too great for continents to slide over oceanic crust. These conclusions and the scientific fashions of the day caused most scientists to reject Wegener's theory of continental drift. However, the physicists' calculations proved only that the mechanism proposed by Wegener was incorrect. They did not disprove, or even consider, the huge mass of evidence indicating that the continents were once joined together. Nevertheless, in the roughly 30-year period between Wegener's death in 1930 and about 1960, continental drift was largely forgotten, although a few persistent geologists continued to report evidence in support of the idea. Much of the hypothesis of continental drift is similar to modern plate tectonics theory. Modern evidence indicates that the continents were together much as Wegener had portrayed them in his map of Pangaea. Today, most geologists recognize the importance of Wegener's contributions as being foundational to the development of plate tectonic theory as it exists today. That the Earth's layers, the energy released by an earthquake travels through Earth as waves. After Wegener died and his theory was mostly forgotten, geologists discovered that both the speed and the direction of these waves change abruptly at certain depths, as the waves pass through Earth. They soon realized that these changes reveal that Earth is a layered planet. Figure 6.4 and Table 6.1 describe the layers. It is necessary to understand the layers of the Earth. The crust is the outermost and thinnest layer. Because it is cool relative to the layers below, the crust consists of hard, strong rock. Crust beneath the oceans differs from that of continents. Oceanic crust is between 4 and 7 kilometers thick and is composed mostly of dark, dense basalt. In contrast, the average thickness of continental crust is about 20 to 40 kilometers, although under some mountain ranges it can be as much as 70 kilometers thick. Continents are composed primarily of granite, which is lighter colored and less dense than basalt. The mantle lies directly below the crust. It is almost 2,900 kilometers thick and makes up 80% of Earth's volume. The mantle is composed mainly of peridotite, a rock that is denser than the basalt and granite of the crust. Although the chemical composition may not vary much throughout the entire mantle, temperature and pressure increase with depth. Figure 6.5a shows that the temperature at the top of the mantle is near 1,000 degrees Celsius and that near the mantle core boundary is about 3,300 degrees Celsius. These changes cause the strength of mantle rock to vary with depth. The differences in strength create layering. Figure 6.5b shows that internal pressure also increases with depth. At this point, it is important to understand the effects of temperature and pressure on rocks. Most people understand that increasing temperature will eventually melt a rock. Less obvious, however, is the fact that high pressure inhibits melting, because rock expands by about 10% when it melts. High pressure makes it more difficult for a rock to expand and therefore impedes melting. If the combined effects of temperature and pressure are close to, but just below, a rock's melting point, the rock remains solid but loses strength, so it becomes weak and plastic. In such a weakened state, rock can flow slowly, similar to the way honey spills from a jar. At that point, if temperature rises or pressure decreases, the rock will begin to melt. Because both temperature and pressure increase with depth in Earth, their combined effects change the physical properties of rocks with increasing depth. These changes create two distinctly different layers in the upper mantle. The strength of the rocks is very different between the two layers, although the composition of mantle rock in each layer is similar. The lithosphere figure 6.5 shows that the uppermost mantle is cool and its pressure is low, conditions similar to those in the crust. Both factors combine to produce hard, strong rock similar to that of the crust. Recall from Chapter 1 that the outer part of Earth, including both the crust and the uppermost mantle, make up the lithosphere. The average thickness of the lithosphere is about 100 kilometers but ranges from about 75 kilometers beneath ocean basins to about 125 kilometers under the continents. The lithosphere, then, consists mostly of the cold, strong uppermost mantle. The crust is just a thin layer of buoyant rock forming the top of the lithosphere. The asthenosphere at a depth varying from 75 to 125 kilometers beneath Earth's surface, the temperature and pressure conditions are close to the melting point of mantle rock. As a result, at this depth the mantle abruptly loses strength relative to the overlying rock and becomes weak and plastic. About 1 to 2% of the rock melts, although the rest remains solid. This weak, plastic, and partly molten character extends to a depth of about 350 kilometers, where increasing pressure overwhelms temperature and the rock becomes stronger again. This layer of weak mantle rock extending from about 100 to 350 kilometers deep is the asthenosphere. The average temperature in the asthenosphere is about 1,800 degrees Celsius, although the temperature increases with depth as it does in other Earth layers. Pressure in the asthenosphere rises from about 35 kilobars near the top to about 120 kilobars at the base. If you apply force to a plastic solid, it deforms slowly, much like the spilled honey. The soft, plastic rock of the asthenosphere behaves in this way, relative to the strong, hard lithosphere that lies on top of it. The lithosphere is not rigidly supported by the rock beneath it, but instead floats on the soft, plastic rock of the asthenosphere. This concept of a floating lithosphere is important to our understanding of plate tectonics and Earth's internal processes. The mantle below the asthenosphere at the base of the asthenosphere, the increasing pressure overcomes the effect of rising temperature, and the strength of the mantle increases again. Although the mantle below 350 kilometers is stronger than the asthenosphere, it is not as strong as the lithosphere, but rather is plastic and capable of flowing slowly over geologic time. The core, as you learned in Chapter 1, the core is the innermost of Earth's layers. It is a sphere with a radius of about 3,470 kilometers, about the same size as Mars, and is composed largely of iron and nickel. The outer core is molten because of the high temperature and relatively lower pressure there. In contrast, the temperature of the inner core is close to 7,000 degrees Celsius, roughly similar to the temperature of the Sun's surface, and the pressure is 3.5 million times that of Earth's atmosphere at sea level. This extreme pressure compresses the inner core to a solid, despite the fact that it is even hotter than the molten outer core. The seafloor spreading hypothesis following the death of Alfred Wegener in 1930, few geologists thought much about continental drift. Most regarded the arrangement of the continents and ocean basins as fixed, and this set of assumptions prevailed through the 1940s and 1950s. The huge naval effort that was involved during World War II set in motion a series of new discoveries about the ocean floor that would ultimately disprove the fixest assumptions about the configuration of the continents and oceans. On the day after Pearl Harbor was bombed, a young Princeton geology instructor named Harry Hess volunteered for active duty in the U.S. Navy. Hess was already in the U.S. Naval Reserves, where he conducted research on the ocean floor using Navy submarines to carry out his experiments. 10 years before the war broke out, Hess had earned his Ph.D. in geology at Princeton and had subsequently joined the faculty there. As a young professor, Hess had participated in submarine-based deep-sea research with preeminent Dutch geophysicist Felix van Maenisch, who had discovered a series of unexplained systematic variations or anomalies in the strength of the Earth's gravity field along the long string of volcanic islands in the East and West Indies. Back at Princeton, Hess decided the best way to carry out similar work of his own was to join the Navy Reserves and carry out his work using U.S. submarines. Once the war began and Hess became an active-duty naval officer, he first worked to estimate the daily positions of German submarines and was later transferred to sea duty, where he took part in several assault landings in the Pacific and eventually captained his own assault transport ship. While Hess was on active sea duty as a naval officer, he conducted a remarkable set of measurements using a special deep-sea fathometer that he had installed on his ship. Hess ordered that the fathometer be kept on all the time and that it print out a continuous chart of the ocean depth during his frequent crisscrossings of the Pacific. Over the course of the war, Hess thus recorded some 250,000 miles of soundings of the ocean floor. Hess's wartime depth transects across the Pacific revealed that the floor of the ocean was covered by numerous flat-topped mountains that rose from the flat deep ocean floor to much shallower depths of 2,000 or 3,000 feet. Hess recognized the features as ancient volcanoes that eventually became inactive and sank beneath the sea surface. As they sank, erosion by wave energy planed off the tops of the volcanoes. Hess called the features geos, named after Arnold Guyot, the Swiss geologist who founded Princeton's geology department after World War II ended. Hess remained in the Navy Reserve where he eventually made the rank of Rear Admiral. Excited by his discovery of geos in the Pacific, he continued to direct his naval research efforts at mapping the sea floor. Years later, the chair of Princeton's geology department while Hess was there was interviewed, and he remarked that following the war, Hess had the whole U.S. Navy working for him as a data collection agency. One of the key results to come of this naval research effort to map the ocean floors after World War II was the observation that the geos that stood closest to the ocean trenches were systematically older and also stood at a slight angle to geos that stood further from the ocean trenches and closer to the mid-ocean ridges. Hess deduced that the geos were transported from the mid-ocean ridges to the ocean trenches by the moving ocean floor. Geos that were closest to the trench were tilted on the steeper slope of the ocean floor there. Hess calculated that the geos were traveling about 5 inches per year. In addition to the geos, mapping the ocean floor during and after World War II revealed the presence of the largest mountain chain on Earth, now called the Mid-Oceanic Ridge System. One branch of this huge submarine mountain range, called the Mid-Atlantic Ridge, lies directly in the middle of the Atlantic Ocean, halfway between North and South America to the west, and Europe and Africa to the east. In 1962, Hess published his paper, History of Ocean Basins, in which he described his ideas about the movements of the ocean floor. The paper was so unusual that Hess described it as an essay in geopoetry. At about the same time, a government geologist Robert Dietz had independently developed the same basic idea and Dietz coined the term seafloor spreading. Both Hess and Dietz proposed convection, the circular movement of a heated substance, like hot air rising in a room, as the driving force behind the moving ocean floor. Building on an idea his Dutch colleague Manish had described many years earlier. Hess suggested that the Earth's mantle was under such extreme heat and pressure that it could move like slowly deforming plastic. In his 1962 paper, Hess also made the following key observations. 1. Rising limbs of convecting mantle are present under mid-ocean ridges. 2. The upwelling mantle accounts for high heat flow observed under the mid-ocean ridges. 3. The entire ocean is virtually swept clean, as it is replaced by new ocean floor every 300–400 million years. This constant replacement of the ocean floor accounts for the relatively thin veneer of sediments in the deep ocean and also accounts for the absence of oceanic crust older than Cretaceous age. 4. The continents are carried passively along by the convecting mantle. They do not plow through oceanic crust. 5. The ocean floor and its thin cover of sediments, as well as all volcanic seamounts and geos, also ride down into the jaw crusher of the descending limb of a mantle convection cell. The 1962 paper by Hess paved the way for much additional research on the ocean basins during the rest of that decade. Among the most intriguing and ultimately revealing observations involved magnetism of the sea floor. As you learned in Chapter 3, oceanic crust is composed mostly of basalt, an igneous rock rich in iron. As basaltic lava cools and forms solid rock, the iron-rich mineral crystals in the basalt operate like weak magnets. The magnetic fields of these minerals align parallel to the Earth's magnetic field. Thus, the basalt preserves a record of the orientation and strength of Earth's magnetic field at the time the rock cools. By towing devices called magnetometers behind their research vessels, oceanographers were able to detect and record magnetic patterns in the basalt forming the deep ocean floors. Figure 6.9 shows the magnetic orientations of seafloor rocks near a part of the Mid-Atlantic Ridge southwest of Iceland. In this figure, purple stripes represent basalt with a magnetic orientation parallel to Earth's current magnetic field, called normal magnetic polarity. The intervening blue stripes represent rocks with magnetic orientations that are exactly opposite to the current magnetic field, called reversed magnetic polarity. Notice that the stripes form a symmetric pattern of normal and reversed polarity about the axis of the ridge, and that the central stripe is green, indicating that basalt at the ridge axis has a magnetic orientation parallel to that of Earth's magnetic field today. Why do the seafloor rocks have alternating normal and reversed polarity, and why is the pattern symmetrically distributed across the mid-oceanic ridge? In the mid-1960s, three scientists, a Cambridge graduate student named Frederick Vine, his professor, Drummond Matthews, and Lawrence Morley, a Canadian working independently of the other two, proposed an explanation for these odd magnetic patterns on the seafloor. They knew that other scientists had been studying the magnetism preserved in layers of basalt forming the Hawaiian Islands and discovered that Earth's magnetic field has reversed its polarity on the average of every 500,000 years during the past 65 million years. The data from Hawaii indicated that when a magnetic reversal of Earth's field occurs, the north magnetic pole becomes the south magnetic pole, and vice versa. Vine, Matthews, and Morley suggested that the symmetrical magnetic stripes they observed in the seafloor were produced by the continuous spreading of newly formed oceanic crust away from the mid-oceanic ridges, like two conveyor belts moving outward, away from each other. They recognized that the seafloor and oceanic crust become older with increasing distance from the ridge axis, exactly as Hess had predicted in his 1962 paper. New basalt lava rises through cracks that form at the ridge axis as the two sides of the seafloor separate. As the lava cools and solidifies, the basalt records the strength and orientation of Earth's field. Because Earth's field periodically reverses, the magnetism preserved in the basalt of the ocean floor acquires a striped pattern. At the same time as these seafloor magnetic patterns were being detected and explained, oceanographers discovered that the layer of mud overlying the seafloor basalt in most parts of the oceans typically is thinnest at the mid-oceanic ridge and becomes progressively thicker at greater distance from the ridge. They reasoned that if mud settles onto the seafloor at the same rate everywhere, and if the ridge is the newest part of the seafloor, the mud layer would be thinnest there. Because oceanic crust is progressively older with increased distance from the ridge axis, more time has elapsed for mud to accumulate, so the layer of mud becomes progressively thicker. The oceanographers also found that fossils in the deepest layers of mud overlying basalt are very young at the ridge axis but become progressively older with increasing distance from the ridge. This discovery, too, indicated that the seafloor becomes older with increasing distance from the ridge axis as had been predicted by Robert Dietz when he coined the term seafloor spreading as a general model for the origin of all oceanic crust. By the end of the 1960s, the seafloor spreading hypothesis became the basis for development of the much broader theory of plate tectonics. The theory of plate tectonics, like many great unifying scientific ideas, the plate tectonics theory is simple. Briefly, it states that the lithosphere is a shell of hard, strong rock about 100 kilometers thick that floats on the hot, plastic asthenosphere. As you learned in Chapter 1, the lithosphere is broken into 7 large segments called tectonic plates. They are also called lithospheric plates or, simply, plates. The terms are interchangeable. The tectonic plates slide slowly over the asthenosphere at rates ranging from less than 1 to about 16 centimeters per year, about as fast as your fingernails grow. Continents and ocean basins make up the upper parts of the lithospheric plates, so as the plates slide over the asthenosphere, the continents and oceans move with them. A plate boundary is a fracture that separates one plate from another. Neighboring plates can move relative to one another at these boundaries in 3 ways, shown by the insets in Figure 6.12. At a divergent boundary, 2 plates move apart from each other. At a convergent boundary, 2 plates move toward each other, and at a transform boundary, they slide horizontally past each other. Table 6.2 summarizes characteristics and examples of each type of plate boundary. The great forces generated at plate boundaries build mountain ranges, cause earthquakes, and produce many of Earth's volcanoes. In contrast, the interior portions of plates usually are tectonically quiet because they are further from the zones where 2 plates interact. Divergent plate boundaries. At a divergent plate boundary, also called a spreading center or a rift zone, 2 plates spread apart from one another, as shown at the center of Figure 6.13. The underlying asthenosphere rises upward to fill the gap between the separating plates. As it rises, the decrease in pressure causes the hot asthenosphere to melt and form magma. As this magma continues to rise, it cools to form new crust. Most of this activity occurs at divergent plate boundaries within the ocean basins, but it also can occur between two continental plates that are rifting apart, as in East Africa. Both the lower lithosphere and the asthenosphere are parts of the mantle and have similar chemical compositions. The main differences between the two layers are in temperature, pressure, and mechanical strength. The cool lithosphere is strong and hard, but the hot asthenosphere is weak and plastic. As the asthenosphere rises closer to Earth's surface between two separating plates, it cools and gains mechanical strength, and therefore transforms into new lithosphere. In this way, new lithosphere continuously forms at a divergent boundary. At a divergent boundary, the rising asthenosphere is hot, weak, and plastic. Only the upper 10 to 15 kilometers cools enough to gain the strength and hardness of lithosphere rock. As a result, the lithosphere rock, including the crust and the upper few kilometers of mantle rock, can be as little as 10 or 15 kilometers thick at a spreading center. But as the lithosphere spreads, it cools from the top downward and thickens. As it spreads outward and cools, the new lithosphere also thickens because the boundary between cool rock and hot rock migrates downward. Consequently, the thickness of the lithosphere increases as it moves away from the spreading center. Think of ice freezing on a pond. On a cold day, water under the ice freezes and the ice becomes thicker. In a similar fashion, the cooling lithosphere thickens to about 75 kilometers beneath ocean basins and to about 125 kilometers beneath continents. The mid-oceanic ridge, rifting in the ocean's new lithosphere at an oceanic spreading center, is hotter than older lithospheric rock farther away from the divergent boundary, and so the new lithosphere has lower density. Therefore, it floats to a higher level, forming the undersea mountain chain called the mid-oceanic ridge system. But as lithosphere migrates away from a spreading center, it cools and becomes denser. As a result, the lithosphere sinks into the soft, plastic asthenosphere, causing the depth of the seafloor to increase with distance from the mid-oceanic ridge. Splitting continents, rifting in continental crust. A divergent plate boundary can split apart continental crust in a process called continental rifting. A rift valley develops in a continental rift zone because continental crust stretches and fractures. Basaltic magma from the base of the crust typically wells up through the newly formed fractures, and some of it reaches the surface to form basaltic volcanism. As the basalt magma works its way through the granitic continental crust, it partially melts it to form additional magma that is rhyolitic in composition. Typically, both basalt and rhyolite compositions erupt from evolving continental rifts. As the continental crust continues to stretch and fracture, and as more basalt is intruded into it or erupted onto it, the surface of the rift begins to sink. As the process continues, eventually the continental crust separates into two sides with a zone of much thinner crust made of basalt in between. Continued rifting along the same zone causes the two sides of the continent to move apart and new oceanic crust to be formed at the active rifting zone located in the middle of the new ocean basin. With time, a narrow oceanic gulf like the Red Sea can spread to become a major ocean. Today, one of the best places to study continental rifting is in eastern Africa, where three converging arms of a rift system collectively are breaking apart the African continent. Separated by about 120 degrees, the three rift arms are the Gulf of Aden, the Red Sea, and the East Africa Rift System. Figure 6.15 shows the relative counterclockwise movements of the Arabian Peninsula away from northeastern Africa as the Red Sea and Gulf of Aden continue to separate. The third arm of the rift, the East African Rift System, projects southward into East Africa, where it is fracturing the crust and causing the development of deep lakes in the Rift Valley adjacent to steep mountains on the rift margins. If this rifting continues, eastern Africa will separate from the main portion of the continent, forming at first a narrow gulf like the Red Sea and Gulf of Aden before widening to form a new ocean between the diverging portions of separated continental lithosphere. Convergent plate boundaries at a convergent plate boundary, 2. Lithospheric plates move toward each other. Not all lithospheric plates are made of equally dense rock. Where two plates of different densities converge, the denser plate sinks into the mantle beneath the less dense one. This sinking process is called subduction and is shown on both the right and left sides of figure 6.11. A subduction zone is a long, narrow belt where a lithospheric plate is sinking into the mantle. On a worldwide scale, the rate at which old lithosphere sinks into the mantle at subduction zones is equal to the rate at which new lithosphere forms at spreading centers. In this way, Earth maintains a global balance between the creation of new lithosphere and the destruction of old lithosphere. Plate convergence can occur between a plate carrying oceanic crust and another carrying continental crust, between two plates carrying oceanic crust, and between two plates carrying continental crust. Convergence of oceanic crust with continental crust. Recall that oceanic crust is generally denser than continental crust. In fact, the entire lithosphere beneath the oceans is denser than continental lithosphere. When an oceanic plate converges with a continental plate, subduction occurs and the denser oceanic plate plunges into the mantle beneath the edge of the continent. As a result, many subduction zones are located at continental margins. Today, oceanic plates are subducting beneath the western edge of South America, along the coasts of Oregon, Washington, and British Columbia, and at several other continental margins shown in figure 6.12. When the descending plate reaches the asthenosphere, large quantities of magma are generated by processes explained in Chapter 8. Magma rises through the lithosphere of the overriding plate. Much of the magma reaches the surface, where it erupts from a chain of volcanoes that form parallel to the subduction zone. Chapter 9 describes how the Andes, a chain of volcanic mountains, formed as a result of the subduction of a Pacific oceanic plate beneath the west coast of South America. The oldest seafloor rocks on Earth are only about 200 million years old, because oceanic crust continuously is being destroyed where it subducts and is melted. In contrast, rocks as old as 4.03 billion years are found on continents because subduction consumes little continental crust. Continental crust generally is too thick to subduct. In addition, continental crust is made of mostly granite, a lower density rock than basalt. Relative to oceanic lithosphere, this lower density provides continental lithosphere with buoyancy and further inhibits its ability to subduct. Convergence of two plates carrying oceanic crust. Recall that newly formed oceanic lithosphere is hot, thin, and of relatively low density, but as it spreads away from the mid-oceanic ridge, it becomes older, cooler, thicker, and denser. Thus, the density of oceanic lithosphere increases with its age. When two oceanic plates converge, the older, denser one subducts into the mantle. Oceanic subduction zones are common in the southwestern Pacific Ocean and also form the Aleutian Islands. The effects of subduction zones on the geology of the seafloor are described in Chapter 15. Convergence of two plates carrying continents. If two converging plates carry continents, the relatively low density of the continental lithosphere prevents either plate from subducting deeply into the mantle. Continental lithosphere does not normally sink into the mantle at a subduction zone for the same reasons that a log does not sink into a lake. Both are of lower density than the material beneath them. Rather, when two plates with continental lithosphere do collide, they crumple against each other and form a huge mountain chain. The Himalayas, the Alps, and the Appalachians all formed as a result of continental collisions. The formation of the Himalayas is described in Chapter 9. Transform plate boundaries. A transform plate boundary forms where two plates slide horizontally past one another as they move in opposite directions. This type of boundary can occur in both oceans and continents and can result in frequent earthquakes. California's San Andreas Fault is a transform boundary between the North American plate and the Pacific plate. The anatomy of a tectonic plate. The nature of a tectonic plate can be summarized as follows. 1. A plate is a segment of the lithosphere, thus, it includes the uppermost mantle and the overlying crust. 2. A single plate can carry both oceanic crust and continental crust. The average thickness of a lithospheric plate covered by oceanic crust is 75 kilometers, whereas that of lithosphere covered by a continent is 125 kilometers. Lithosphere is thinnest at oceanic spreading centers and thickest where continent collisions are taking place. 3. A plate is composed of hard, mechanically strong rock. 4. A plate floats on the underlying hot, plastic asthenosphere and slides horizontally over it. 5. A plate behaves like a slab of ice floating on a pond. It may flex slightly, as thin ice does when a skater goes by, allowing minor vertical movements. In general, however, each plate moves as a large, intact sheet of rock. 6. Plate margins are tectonically active. Earthquakes, mountain ranges, and volcanoes are common at plate boundaries. In contrast, the interior of a lithospheric plate normally is tectonically stable. 7. Tectonic plates move at rates that vary from less than 1 to about 16 centimeters per year. Continents and oceans are carried on the upper parts of the moving lithosphere and migrate across Earth's surface at the same rates at which the plates move. For example, because of seafloor spreading in the mid-Atlantic ridge system, Manhattan Island is now 9 meters farther from London than it was when the Declaration of Independence was written in 1776. Alfred Wegener was correct in saying that continents drift across Earth's surface. Why plates move? The Earth as a heat engine. After geologists had developed the theory of plate tectonics, they began to ask, why do the great slabs of lithosphere move? Research has shown that subduction can continue slowly all the way to the core, mantle boundary, to a depth of 2,900 kilometers. At the same time, hot rock rises from the deep mantle toward the surface to replace the lithosphere lost to subduction. The term convection refers to the circulating flow of fluid material in response to heating and cooling. The process of mantle convection continually stirs the entire mantle as rock that is hotter than its surroundings rises toward Earth's surface and old plates that are colder than their surroundings sink into the mantle. In this way, the entire mantle, lithosphere system slowly circulates in cells that carry rock from as deep as the core, mantle boundary toward Earth's surface and then back into the deepest mantle. A soup pot on a hot stove illustrates the process of convection. Rising temperature causes most materials, including soup, to expand. When soup at the bottom of the pot is heated by the underlying stove, it becomes warm and expands. It then rises because it is less dense than the soup at the top. When the hot soup reaches the top of the pot, it flows along the surface until it cools and sinks. Although the circulation of soup in a hot pot provides a good illustration of convection, the circulation of the mantle is considerably more complex than that. Not only is the mantle not shaped like a pot, but the circulation of the mantle is driven by 3 processes: heat from the core below, radioactive decay of unstable isotopes within the mantle, and the cooling of the upper surface that is in contact with the lithosphere. Today, the specifics of mantle convection are not well understood, although there is general agreement that mantle convection and plate tectonics are part of the same system and that mantle convection is the main mechanism for transport of heat away from Earth's interior to the surface. What is less certain is the structure of the circulating mantle rock. For example, upwelling of hot mantle beneath mid-ocean ridges is quite shallow and not related to deep mantle circulation. In this case, it appears to be the diverging motion of the lithospheric plates that causes upwelling of mantle from shallow depths, and not the other way around. 2 other processes, shown in Figure 6.17, may facilitate the movement of tectonic plates. Notice that the base of the lithosphere slopes downward from a spreading center. The grade can be as steep as 8%, steeper than most paved highways. Calculations show that even if the slope were less steep, gravity would cause the lithosphere to slide away from a spreading center over the soft, plastic asthenosphere at a rate of a few centimeters per year. This downslope sliding of the lithosphere away from a spreading center is called ridge push and may contribute to the movement of plates. As the lithosphere moves away from a spreading center and cools, it becomes denser. Eventually, old lithosphere may become denser than the asthenosphere below. Consequently, it can no longer float on the asthenosphere and sinks into the mantle in a subduction zone, pulling the trailing plate along with it in a phenomenon referred to as slab pull. Both ridge push and slab pull are considered to contribute to the movement of a lithospheric plate as it slides over the asthenosphere. Mantle plumes and hot spots. In contrast to the huge, ridge-shaped mass of mantle that rises beneath a spreading center, a mantle plume is a relatively small rising column of plastic mantle rock that is hotter than surrounding rock. Some plumes appear to rise from great depths in the mantle, probably because small zones of rock near the core, mantle boundary become hotter and more buoyant than surrounding regions of the deep mantle. Others form as a result of heating in shallower portions of the mantle. As pressure decreases in a rising plume, rock melts to form magma. The rising heat and magma produce a hot spot in the upper mantle, which in turn heats the overlying lithosphere, forming a volcanic center. The Hawaiian island chain is an example of a volcanic center over a hot spot. As demonstrated by the destructive lava flows on the island of Hawaii in 2018, which destroyed dozens of homes, roadways, and farmland and even struck a boat of tourists with falling lava, the hot spot is very active and poses a constant hazard to its residents. The volcanic center is in the middle of the Pacific tectonic plate because the plume originates deep in the mantle, far from any plate boundary and below the level of lateral plate motion. Some researchers have suggested that the mantle consists of two primary layers, with each layer undergoing convection. The shallower layer, located above 660 kilometers in depth, behaves dynamically and is characterized by relatively rapid convection. Below 660 kilometers, convection is more sluggish. This two-layered mantle model explains why the chemical composition of basalts from mid-ocean ridges is different than those that erupt at hot spots such as Hawaii. Basalt erupting at mid-ocean ridges is part of the shallow convection system, where the mantle is well mixed. In contrast, the basalts erupting in Hawaii are more primitive and come from a plume of mantle welling up from the deeper convection system. Although the two-layered convection model explains some observations, it is not consistent with others. For example, seismologists have been able to use variations in the velocity of earthquake waves passing through the mantle to identify zones of cooler temperature, attributed to mantle downwelling or old subducted oceanic lithosphere. These data suggest that the relatively cool remnants of some subducted slabs extend completely through the mantle to the core, mantle boundary. Supr prior to 2 billion years ago, large continents as we know them today may not have existed. Instead, many, perhaps hundreds, of small masses of continental crust and island arc similar to Japan, New Zealand, and the modern islands of the southwest Pacific Ocean probably dotted a global ocean basin. Then, between 2 billion and 1.8 billion years ago, tectonic plate movements brought these microcontinents together to form a single landmass called a supercontinent. After a few 100 million years, this supercontinent, called Nuna, developed rifts and broke into fragments. The fragments then separated, each riding away from the others on its own tectonic plate. About 1 billion years ago, the fragments of continental crust reassembled, forming a second supercontinent, called Rodinia. In turn, this continent fractured and the continental fragments reassembled into a third supercontinent about 300 million years ago, 70 million years before the appearance of dinosaurs. This third supercontinent is Alfred Wegener's Pangaea, which began to break apart about 235 million years ago, in late Triassic time. The tectonic plates have continued their slow movement to create the mosaic of continents and ocean basins that shape the map of the world as we know it today and will continue to shape it into the future. One recent model of future plate motion suggests that the current configuration of continents will rearrange to form the next supercontinent, named Amasia, about 100 million years from now, near the present-day North Pole. Isostasy, vertical movement of the lithosphere. If you have ever used a small boat, you may have noticed that the boat settles in the water as you get into it and rises as you step out. The lithosphere behaves in a similar manner. If a large mass is added to the lithosphere, the underlying asthenosphere flows laterally away from that region to make space for the settling lithosphere. But how is mass added or subtracted from the lithosphere? One process that adds and removes mass is the growth and melting of large glaciers. When a glacier grows, the weight of ice forces the lithosphere downward and causes the asthenosphere to move laterally away from the depressed region. For example, the Hudson Bay region of Canada was depressed during the last glaciation by an ice sheet about 3,000 meters thick. Conversely, when a glacier melts, the continent rises, or rebounds. Because the rate of rebound is slower than the rate at which the ice melts, the surface formerly below thick glacial ice can remain depressed for thousands of years after all the ice is gone. Thus, the Hudson Bay region of Canada remains below sea level, although it is rising at a rate of about 1 centimeter per year as the underlying asthenosphere slowly flows back into the region. The Great Lakes, located near the former southern margin of the ice sheet, also are slowly rebounding following the melting of glacial ice. The rebound is faster on the northern side of the lakes because the ice was thicker there. Similarly, in Scandinavia, geologists have discovered Ice Age beaches that are tens of meters above modern sea level. The beaches formed when glaciers had depressed the Scandinavian crust to sea level, but they now lie well above that elevation because the land rose as the ice melted. The concept that the lithosphere is in floating equilibrium on the asthenosphere is called isostasy, and the vertical movement in response to a changing burden is called isostatic adjustment. The iceberg pictured in figure 6.20 illustrates an additional effect of isostasy. A large iceberg has a high peak, but its base extends deeply below the water's surface. The lithosphere behaves in a similar manner. Continents rise high above sea level, and the lithosphere beneath a continent has a root that extends as much as 125 kilometers into the asthenosphere. In contrast, most ocean crust lies approximately 5 kilometers below sea level, and oceanic lithosphere extends only about 75 kilometers into the asthenosphere. For similar reasons, high mountain ranges have deeper roots than do low plains, just as the bottom of a large iceberg is deeper than the base of a small one. How plate tectonics affect Earth's surface. The movements of tectonic plates generate volcanic eruptions and earthquakes, which help shape Earth's surface. They also build mountain ranges and change the global distributions of continents and oceans. Tectonic activities strongly affect our environment in other ways by impacting global and regional climate, the atmosphere, the hydrosphere, and the biosphere. Volcanoes. Most of Earth's volcanoes result from plate movements. At a divergent boundary, hot asthenosphere oozes upward to fill the gap left between the two separating plates. Portions of the rising asthenosphere melt to form basaltic magma, which erupts onto Earth's surface. Thus, the mid-oceanic ridge is in part a chain of submarine volcanoes. Volcanoes are common in continental rifts as well. For example, the longest continuously erupting lava lake in the world occurs at the volcano Erta Ale, located in Ethiopia within the northern portion of the East Africa Rift System. Numerous other large volcanoes are scattered down the East Africa Rift System for over 1,000 kilometers today. A large portion of western interior North America also is undergoing continental rifting with accompanying volcanism, although there the rifting and volcanics both are spread out over a larger region than in the comparatively narrow East African Rift System. The ongoing rifting in western North America has produced a geologic province called the Basin and Range, which reaches from north of the Canadian border to south of the Mexican border and from the Wasatch Front of Utah to the eastern Sierra Nevada of California. Figure 6.22. The Basin and Range is so named because the extension has broken the crust into numerous tilted segments. The high elevation parts of each segment form isolated ranges, and erosion of each range produces an abundance of sediment that fills in the lower elevation basins. Volcanics within the basin and range include mafic basalt, derived from the base of the crust, and felsic rhyolite, derived from partial melting of the granitic crust by the rising hot basaltic magma. In addition to continental or oceanic rift systems, huge quantities of magma also form in the descending lithosphere of a subduction zone. Some of the magma solidifies within the crust, and some erupts at the Earth's surface from a chain of volcanoes that forms parallel to the subduction zone. In North America, the Cascade Range in the Pacific Northwest and Canada is a group of volcanoes that collectively form such a chain. The Aleutian Islands of Alaska, the Andes Mountains in South America, and the volcanic islands of the Caribbean and the West Pacific Ocean all are examples of volcano chains formed in this manner. Earthquakes. Earthquakes are common at all three types of plate boundaries but are generally uncommon within the interior of a tectonic plate. As a result, changes in the land's surface resulting from earthquakes are most common near plate boundaries. Quakes concentrate at plate boundaries simply because the slippage of one plate relative to its neighbor is rarely smooth and continuous. Rather, stress builds up along the plate boundary and is stored in the rock as energy. Eventually, the stress level causes the rock to suddenly break, releasing the stored energy and causing rock on one side of the break to lurch violently past rock on the other. An earthquake is the vibration of the rock due to this sudden movement and rapid release of energy. During a single earthquake, the ground surface can be broken, forming a topographic feature called a scarp. Earthquakes also can cause major landslides and even change the course of rivers and streams. We will learn more about earthquakes in the next chapter. Mountain building. Great chains of volcanic mountains form at rift zones because the new, hot lithosphere floats to a high level and large amounts of magma form in these zones. Along subduction zones, long, linear mountain chains form as magma from the descending oceanic lithosphere melts and some of it ascends to the surface. If two continents collide at a convergent plate boundary, the ground surface will rise for the same reason that a mound of bread dough thickens when you compress it from both sides. Such continent collisions thrust great masses of rock upward, creating huge mountain chains such as the Himalayas, the Alps, and the Appalachians. How plate tectonics affect Earth's climate. The tectonic movements of the continents and the opening and closing of ocean basins through rifting and subduction profoundly alter Earth's oceanic and atmospheric systems. Ocean currents carry warm water from the equator toward the poles, and cool water from polar regions toward the equator, warming polar regions and cooling the tropics. Similarly, winds transport heat and moisture over the globe. Changes in ocean currents and wind patterns, in turn, have far-reaching consequences for regional climate. For example, widespread glaciation across Antarctica began between 38 and 28 million years ago as seafloor spreading caused the continent to drift further away from the southern tips of South America, Africa, and Australia. These tectonic movements not only isolated Antarctica over the South Pole but also established the Antarctic Circumpolar Current, a strong west-to-east ocean current that continuously flows in a clockwise direction around the continent. As it formed, this current prevented warmer water from the southern Atlantic, Pacific, and Indian Oceans from reaching Antarctica, effectively putting the continent into a deep freeze that continues today. Tectonic movements also have altered the composition of the atmosphere and oceans, producing major changes in global climate. For example, some scientists have proposed that the Cenozoic uplift of the Tibetan Plateau in Asia, the largest such uplift in the world, caused a strengthening of the Asian monsoon that led to Earth's recent glaciations. According to this idea, the additional monsoonal rainfall and widespread exposure of new rock as the plateau was uplifted significantly increased the rate of chemical weathering of silicate minerals, including those containing calcium. Once in solution, the calcium ions combined with two anionic groups to form calcium carbonate, CaCO. The 2 was supplied by atmospheric CO that dissolved in ocean water and changed to 2-. In this way, CO, a greenhouse gas, was removed from the atmosphere, causing the Earth to cool and contributing to the development of major glaciations during late Cenozoic time. With these changes in environments and climates come changes in the ecosystems supported by them, thus, tectonic processes also affect the biosphere. Streams and drainage patterns must respond to changes in slope direction and altered distributions of precipitation. Lakes may dry up, or new lakes form. Ultimately, plants and animals may die or migrate away, to be replaced by new species that are adapted to the new climatic conditions. Chapter 7, Earthquakes and the Earth's Structure. Introduction. As we learned in Chapter 6, the Earth's tectonic plates slide slowly over the soft asthenosphere, about as fast as your fingernails grow. Friction often holds the two sides of a plate boundary locked together. Rocks stretch and compress across the boundary as forces build, but otherwise nothing big happens for long periods of time that can range from decades to multiple millennia. Then, suddenly, the two sides of the boundary snap free, releasing all at once the energy that had built up over time and causing an earthquake. An earthquake is a classic example of a threshold effect. The interiors of plates move at a steady rate, but motion is constrained at plate boundaries, causing rocks there to slowly accumulate energy from ongoing plate movements. Once the threshold level of energy has accumulated, it is suddenly and cataclysmically released as an earthquake. Anatomy of an earthquake. Rock appears rigid, but if you apply enough stress, rock will deform. When stress is applied to a rock, the rock can deform in one of three ways: elastically, by fracturing, or plastically. Under small amounts of stress, the rock deforms elastically. If the stress is removed, the rock returns to its original size and shape. A rubber band deforms elastically when you stretch it. The energy used to stretch the rubber band is stored in the elongated rubber. When the stress is removed, it springs back and releases the stored energy. In the same way, an elastically deformed rock will spring back to its original shape and release its stored elastic energy when the force is removed. However, like a rubber band, every rock has a limit beyond which it cannot deform elastically. Under certain conditions, an elastically deformed rock may suddenly fracture. When large masses of rock in Earth's crust deform elastically and then fracture, vibrations are formed that travel through Earth and are felt as an earthquake. Under other conditions, when its elastic limit is exceeded, a rock continues to deform, like the bending of a steel nail. This behavior is called plastic deformation. A rock that has deformed plastically keeps its new shape when the stress is released and, consequently, does not store the energy used to deform it. Therefore, earthquakes do not occur when rocks deform plastically. Figure 7. 1 shows an example of asphalt pavement that fractured during an earthquake. The elastic limit of the pavement was exceeded, so it suddenly ruptured. In contrast, Figure 7.2 shows a rock outcrop that was deformed plastically by forces deep within Earth's crust. Parallel rock layers were bent and twisted into an S-shaped fold over time while the rocks were hot and under pressure. We learned in Chapter 6 that Earth's lithosphere is broken into 7 large and several smaller tectonic plates. Although tectonic plates move at rates between 1 and 16 centimeters per year, friction prevents the plates from slipping past one another continuously. For time frames ranging from decades to millennia, the cool, strong rock near the plate boundary can stretch or compress elastically, while the edges remain locked and immobile. This elastic deformation strains the rock, causing potential energy to build, just like the stretched rubber band or a compressed spring. Then, when the strain reaches a critical threshold, rock suddenly fractures and movement occurs across the fracture, releasing all at once the energy that had built up previously. The ground rises and falls and undulates back and forth. Buildings topple, bridges fall, roadways break, and pipelines snap. An earthquake is a sudden motion or trembling of earth caused by the abrupt release of energy that is stored in rocks. When a rock fracture ruptures during an earthquake and rock on the two sides of the fracture move relative to one another, the fracture becomes a fault. Most movement of crustal rock occurs due to slippage along established faults because the friction binding the two sides of the fault is weaker than the rock itself. As additional tectonic stress then builds and strain begins to accumulate in the rock again, it is more likely to move along the existing fault than to crack somewhere else and create a new fault. However, new faults can form if the orientation and curvature of the existing faults no longer can most efficiently release stress that builds in the rock. Many faults develop as part of a larger group of faults that together release much of the strain that accumulates in a region. For example, thousands of separate normal faults exist today in the North American Basin and Range Province, introduced in Chapter 6. Many of these faults form the geologic boundary separating each mountain range from its adjacent basin. The faults develop through time as the crust extends, tilting large blocks of it. As extension continues, the curved geometry of the first faults to develop makes them no longer the easiest way for the rocks to continue to accommodate the stretching. New faults develop with different orientations and the old faults no longer are active. Although individual faults become active and inactive over geologic timescales, over historical timescales, once a fault is recognized as active, it is presumed to remain so. Many historic earthquakes occur along established faults as strain is suddenly released. For example, the San Andreas Fault in Southern California lies along a tectonic plate boundary that has slipped many times in the past and will certainly again in the future. The boundary includes numerous individual faults, some of which are active and some of which are not. Although much of the movement across the plate boundary is accommodated by the San Andreas, other faults also contribute and some have significant earthquake risk associated with them. For example, the UC Berkeley football stadium is bisected by the Hayward Fault, which in places is slipping a rate of 5 mm per year. The Hayward Fault last generated an earthquake with estimated 7.0 magnitude in 1868 and is considered by the USGS to be the most likely to generate a magnitude 7.0 or greater earthquake within the next 30 years. For comparison, the San Andreas Fault, located across the San Francisco Bay Area from the Hayward Fault, is estimated to have only a 21% chance of generating a magnitude 7.0 earthquake over the same timeframe. During an earthquake, rock moves from a few centimeters to several meters. A single earthquake makes only small changes in the topography or geography of a region. But over tens of millions of years, the relentless motion of plates, accompanied by hundreds of thousands of earthquakes, changes the surface of the planet. In this way, mountains are raised, continents are split apart, and new ocean basins are formed. Earthquake waves when buying a watermelon. One trick is to tap the melon gently with your knuckle. If you hear a sharp, clean sound, it is probably ripe. A dull thud indicates that it may be overripe and mushy. The watermelon illustrates 2 points that can be applied to Earth. The energy of your tap travels through the melon, and the nature of the melon's interior affects the quality of the sound. A wave transmits energy from one place to another. A drumbeat travels through air as a sequence of waves, the sun's heat travels to Earth as waves, and a tap travels through a watermelon in waves. Waves that travel through rock are called seismic waves. Earthquakes and explosions produce seismic waves. Seismology is the study of earthquakes and the nature of Earth's interior based on evidence from seismic waves. The initial rupture point, where abrupt movement creates an earthquake, typically lies below the surface at a point called the focus. The point on Earth's surface directly above the focus is the epicenter. An earthquake produces 2 main types of seismic waves. Body waves travel through Earth's interior and carry some of the energy from the focus to the surface. Surface waves then radiate from the epicenter and travel along Earth's surface, somewhat like swells on the surface of the sea. Body waves. Body waves can be of 2 main types. P waves travel fast and are the first or primary seismic waves to reach an observer. They are compressional elastic waves that cause the rock to undergo alternating compression and expansion. Consider a long spring such as the popular slinky toy, with one end attached to a wall. If you stretch and then rapidly push the end of the slinky, a compressional wave travels back and forth along its length. Each segment of the spring is compressed and then stretched as the wave passes by, so an ant sitting on the slinky would move toward, then away, from the wall. Thus, the wave vibrates in the direction in which it propagates. P waves travel through air, liquid, and solid material. Next time you take a bath, immerse your head until your ears are under water and listen as you tap the sides of the tub. You are hearing P waves. P waves travel at speeds between 4 and 7 km per second in Earth's crust and about 8 km per second in the uppermost mantle. For comparison, the speed of sound in air is only 0.34 km per second, and the fastest jet fighters fly about 0.96 km per second. S waves, the other type of body waves, are slower than P waves and thus are the secondary waves to reach an observer. Also called shear waves, S-waves have a shearing motion that can be illustrated by tying a rope to a wall, holding the opposite end, and giving the rope a sharp up and down jerk. Although the wave travels or propagates parallel to the rope, each segment of the rope moves at right angles to the rope length, so an ant sitting on the rope would move up and down as the wave passes by. A similar motion in an S-wave produces shear stress in a rock, stress that acts in parallel but opposite directions, and gives the wave its name. S-waves vibrate at right angles to the direction in which the wave is moving and travel between 3 and 4 kilometers per second in the crust. Unlike P-waves, S-waves move only through solids. Because molecules in liquids and gases are only weakly bound to one another, they slip past each other and thus cannot transmit a shear wave. Surface wave. Surface waves travel more slowly than body waves. Surface waves undulate across the ground like the waves that ripple across the water when you throw a rock into a calm lake. Two types of surface waves occur simultaneously, an up and down rolling motion called Rayleigh waves and a side-to-side vibration called Love waves, both named after the scientist who first described each wave type. During an earthquake, Earth's surface rolls like ocean waves and writhes from side to side like a snake. Measurement of seismic waves. A seismograph is a device that records seismic waves. In early seismographs, a heavy weight was suspended from a spring. A pen attached to the weight was aimed at the zero mark on a piece of graph paper. The graph paper was mounted on a rotating drum that was attached firmly to bedrock. During an earthquake, the graph paper jiggled up and down, but inertia kept the weight and its pen stationary. As a result, the paper moved up and down beneath the pen, while the rotating drum recorded this earthquake motion over time. This physical, written record of earth vibration is called a seismogram. Modern seismographs use a coil fixed to a pendulum that is suspended in a magnetic field. When an earthquake causes the pendulum to move within the magnetic field, it creates an electric current that is amplified and recorded by a computer. Today, the computer recording seismic wave information is part of the World Wide Web, where it is instantly available to seismologists. The USGS hosts a large earthquake monitoring network, and information from thousands of deployed seismographs around the world is available as soon as it happens. Basic information provided on the monitoring network includes location, magnitude, and depth of each earthquake. For example, within the hour before this sentence was written, a total of 15 earthquakes were recorded globally. 10 were on the island of Hawaii and probably related to the ongoing eruptions there. Seismologists are able to use information from the worldwide network of seismographs to study the details of specific earthquakes, especially the largest ones. One such study is called finite fault modeling, which provide a description of the dynamics of the faulting event that caused the earthquake. Included in the finite fault model are estimates of the total slip distance that occurred on the fault during the earthquake, how much surface area on the fault was involved, and how long the slipping lasted. The USGS has finite fault model results for all of the largest earthquakes to occur over the past several years. Figure 7.13 shows an example of the finite fault model for the devastating March 9, 2011 Tohoku earthquake in Japan. In addition to information available directly through the USGS Earthquake Hazards Program, many excellent third-party web platforms for viewing and sharing maps and information about the most recent earthquakes are available. Measurement of earthquake strength over the past century. Geologists have devised several scales to express the strength of an earthquake. Before seismographs became widespread, geologists evaluated earthquakes on the Mercalli scale, which measures the intensity of an earthquake and is based on structural damage. On the Mercalli scale, an earthquake that destroyed many buildings was rated as more intense than one that destroyed only a few. However, this system did not accurately measure the energy released by a quake because structural damage also depends on distance from the focus, the rock or soil beneath the structure, and the quality of construction. In 1935, Charles Richter devised the Richter scale to express the amount of energy released during an earthquake. Richter magnitude is calculated from the height of the largest earthquake body wave recorded on a specific type of seismograph. The Richter scale is more quantitative than earlier intensity scales, but it is not a precise measure of earthquake energy. A sharp, quick jolt would register as a high peak on a Richter seismograph, but a very large earthquake can shake the ground for a long time without generating extremely high peaks. Thus, a great earthquake can release a huge amount of energy that is not reflected in the height of a single peak and that is not adequately expressed by Richter magnitude. Modern equipment and methods enable seismologists to measure the amount of movement and the surface area of a fault that moved during a quake. The product of these two values and the shear strength of the faulted rock allow them to calculate the moment magnitude. Most seismologists now use moment magnitude rather than Richter magnitude, because